And then our next step is to define a class. Here we name it my model. So this can be any name actually, but we have to use the nn.module class as its parent. I think it's called subclassing. I'm not super familiar with the terminologies, but you get the idea here. Um, so this should have two different classes, two different methods inside this class. One is the init method, and the other one is the forward method. In the init method, we define all the layers of the neural network. And in the forward method, we define how the data flows through this network. So basically, any neural network can be thought of as as a sequence of neural network layers with some non-linearities, which is transforming the input data into multi-dimensional space. So basically, it's just we can think of this um, as the data passing through the network and changing its shape. That's one way to think about it. So here in this specific example, we have three different layers. We are calling that FC1, FC2, and FC3. All of these are linear layers, which are basically they transform, or they basically project the input of 64 dimensions to 128 dimension in this example. And the second layer, the FC2 layer, is again a linear layer. It projects from 128 dimension to again 128 dimension. And the FC3 layer projects from 128 dimension to 3 dimensions. So it's kind of we can think of this as just a one way to think of it is as a black box where the input size is 128 and the output size is 3. And what goes on inside this black box is essentially matrix multiplication with weights and biases. We really don't need to think about it or write code for that because PyTorch already takes care of all these things. And when we initialize these layers, PyTorch already initializes the weights and biases of the network. So we don't really need to take care of this. And if we move beyond PyTorch and go to other libraries like TensorFlow, the idea is very similar. In fact, I think the same class kind of approach is available in TensorFlow 2.0. So everything, almost everything stays the same. Just the syntax changes a bit. Um, then we have the forward method, which is basically how the data passes through the neural network. So we defined a few layers. Actually, we defined two other layers here, ReLU 1 and ReLU 2. These are just nonlinear functions which don't have any parameters in themselves. They don't have any learnable parameters at all. But they are just, we can think of them as nonlinear functions. So specifically, ReLU is a function where if we give in a positive number, the output is the same. And if we give in a negative number, the output is 0. So it basically clips everything to 0 if it is negative. So let's see what we are doing when we pass this data through the network. So the data that we are passing is X here. And X gets, basically it passes through FC1, then the ReLU layer, and we get the output. Then it passes through FC2, followed by the ReLU nonlinearity, and finally it passes through FC3. So if we do the calculation, so X should be of dimension 128 in this case. Actually, X should be of dimension 64 in this case. It gets transformed to 128 dimensional vector. And then from 128 dimensional vector, it again gets transformed to the same number of dimensions, 128. And finally, after passing through FC3, it gets transformed into three-dimensional vector, and that's what is returned here. So the point here is that we need to be able to like um, uh, change the dimension of the data to the number of classes that we have. So in this case, we have three different classes, um, and that's why the final number of dimensions is 3. Now we will see a real example in the demo section of this presentation, but this is an example how we define or basically build a model which is not scikit-learn based, but rather it's a neural network based model. And once we have the class definition, we can just initialize the model by uh, just doing my model, exactly the name that we um, gave to our class. And that's how we initialize the model. Just kind of a quick recap that in case of um, scikit-learn models, the model building part is almost always taken care of. We just need to initialize it. But in case of um, neural network based models, most of the times we need to define the whole model ourselves and then initialize it. Um, we'll see a few examples in the demo section. So now what we have built the model, we have the pre-processed data, and obviously the next step is to feed the data into the model to do something. What is that something? That's training, right? We basically want to train our model using the data. So let's see how to do that in the first case, which is the scikit-learn based models. Let's say we have a logistic regression model which we have initialized. It's a very straightforward process to train the data, to train the model using the existing data. It's just one line, basically model.fit, and X and Y. X are basically all the feature columns combined together, and Y is just the label column. So X is a matrix, Y is just a vector. We should make sure that Y is a vector, not a matrix. Um, and this is how we train the model. It's just dot fit. It takes care of everything which goes under the hood. And after the model is trained, we can predict using this trained model by just using model.predict, and we can just give the features as input from the test data or maybe from the development data, and we can get the predicted labels. So this is how we do prediction, like training and prediction in case of scikit-learn. As you can see, it's very straightforward, and this kind of generalizes to almost all the scikit-learn based models. So it's pretty handy to just use the same code for any classifier that we build. When it comes to a neural network based classifier, though, we should write the training loop by ourselves. So what really happens in case of a neural network based training is that we take the data, we pass the data through the neural network multiple times until the model has learned how to do the tasks. So that's the general idea how a neural network is trained. And also, while doing the training, instead of feeding all the data at once, we usually feed the data in batches. So if we have 1 million data samples, for example, we feed batches of, let's say, just 100 samples at once, and we keep on training the model with batches, and we keep on doing that until we see some kind of convergence criterion is met. So that's the general idea of how we train a neural network, and the code here shows exactly the same thing. And here the variable epoch is used to kind of just loop over all the epochs we want to train our model for. And epoch is basically the number of times the whole data set passes through the neural network while the training process. So in this case, it's set to num epochs, capital num epochs, and we loop through this. And for each epoch, we loop through all the batches in that epoch. So I think some of this will become more clear when we look at the example at the end during the demo session. But the main idea is that we need to train the model for multiple epochs, and for each epoch we need to train it for different batches. And once we are inside this inner for loop, we go through a series of steps which are important for the model to actually train. The first step is to zero out the gradients of the optimizer. So what is the optimizer? We will look at that in the demo session. It's basically some, as the name suggests, it optimizes the weights of the neural network and kind of makes it learn whatever we are trying to train it to do. But it's important to uh, zero out all the gradients of the optimizer. So this is a PyTorch kind of lingo here. It probably does not exist in other deep learning libraries, but this is an important step. Then we do a forward pass of the data. Here, it's just like just passing the whole batch of data through the model. We don't need to, so this essentially is the forward function that we wrote earlier. So just going back to the previous slide here. So the forward method here, whatever happens in the forward method, it's exactly that's exactly what happens when we do the forward pass here. And as the name suggests, that's why we named it the forward method. Uh, so we store the output in the variable out here in this case. Once we have passed the batch of data through the model, we are now ready to compute the loss for that batch. And we cannot compute the loss with just the model predictions. We need to use the original labels, or we can call them goal labels, to compute the loss. And the loss can be computed using different criteria, and we can use one criterion out of all those possible options. So let's call that criterion. That's the method which computes the loss, and this takes in the model outputs from the forward pass and also the goal labels, which are denoted here as batch y. And once we pass these two entities to the criterion, we compute a loss. Loss is no longer a vector or a matrix. It's just a scalar number. It's just a like value. Like let's say loss is 20.5. So it's just a scalar value. Um, and once we have the loss, we can do the back propagation, which is how neural networks are trained. And in PyTorch, it's just loss dot backward. This takes care of the back propagation step completely. And once we have done the back propagation, we go to the optimizers or updating the model weights. That's how the model actually learns, by changing the weights little by little every time we see a new batch, until the model gets confident to classify new samples, basically. So the optimizer dot step finally makes sure that the model weights are updated. And since this is the inner for loop, this goes on for all the batches in the data, and the whole process is repeated for as many times as the num epochs. So this is kind of the whole model training process. The idea stays the same for prediction phase as well, when the model is already trained, but we just want to predict using the model. It's just that in that phase, we don't compute the loss, we don't do the back propagation or the optimizer step. We just do the forward pass and get the model outputs. So we'll see an example at the end. So I don't know if I'm just running over time. Let me make sure. Okay, so hopefully I'm in time. Let me go to the next slide now. So now we have the model training part also. Um, there is one important piece still missing, which is how do we evaluate the model. So that's the next part. I'm going to make the font larger. Okay, so we have the whole data set, pre-processed it, build the model, then trained the model, and also predicted using the trained model. Then we need to be able to uh, evaluate how good is our model, so that we actually know if the model has learned to do whatever we were trying to train it to do. Plus, at the same time, it is, if we have different approaches, let's say we have method 1, method 2, method 3, we can compare which method is better than the others, which method is the best. So in this case, obviously, as you can, you might be familiar with accuracy, right? Which is just how many out of, let's say, the 100% of the test samples, how much percentage did the model get right? That's the accuracy. But accuracy is not a great metrics when the data is imbalanced, which means there are different number of samples for different classes. In those cases, it is recommended to use other metrics like precision and recall, and also F1 score. All these metrics, higher is better. So we should aim for higher precision, higher recall, and higher F1 scores. So the picture on the right shows the how we compute precision recall, and also what is their underlying meaning. True positives, true negatives, false positives, false negatives, these are the four categories of samples after we have done the prediction. So using these four categories, we can compute all these values. And F1 score, usually it's recommended to use the F1 score instead of the accuracy when the data is imbalanced. Um, but if the data is balanced, accuracy is still a good number. But if the data is imbalanced, we should make sure to look at the F1 score in addition to the accuracy, because accuracy can be misleading. So I'll give this as a thought experiment. Think about a case where accuracy is misleading, and at the end of the presentation, we can, if you think of a scenario where accuracy is misleading and F1 score is not, so let me know. Um, and this is how we can, this is how easy it is to compute all these numbers. The formula that we saw in the previous slide, we don't need to write them in code because there is division by zero and all these things we need to take care of. So it's already available in scikit-learn metrics, and we can just import them from scikit-learn. So moving on, so I'll just spend 1 minute before handing it over to Somendra. So once we have done all of these experiments, it's useful to at least visualize, try to see what's going on. And this is just revisiting pandas here, where we can use the df.plot, and there are multiple options to plot different kind of plots, histogram plots. We can use this to analyze the original data or even the results, for example, the predictions. Here are some useful functions. I think the font size is very small, but basically um, uh, the value counts function gives us the count of unique values. The length of the data frame gives us the number of rows. Df.shape gives us how many rows and columns. Unique gives us the number of distinct values in a column. And describe is a good function to do a descriptive and statistical analysis kind of for each feature. There was a great data visualization tutorial. I just linked it here, which is part of this tutorial series. So check that out. I have linked it in the slides. So I will hand it over to Samendra now.
Yeah, thank you, Subhadasi. Let me share my screen. Okay, so we have discussed all these topics and the procedures on what are the ML steps we need to do. So these are like data loading, pre-processing, feature selection, model building, training and evaluation, and these all things. Um, uh, there is high level of abstraction has been done over in last few years. Like you can automatically do machine learning. So if I give one example, there is the first one like AutoKeras. This is one library. So here what you can do is like in this 4 lines, you can do a machine learning prediction. So you need to do first import AutoKeras as AK, then you define a model, not model, define the classifier. So and like ak.image classifier. So you want to do image classification. Then you split your data set into train and test. So X train is the input and Y train is the label which you want to predict. And the results are like based on that CLF fit is like it will train the model using this train label input and output labels. Then the results it will show here like CLF predict X test. So yes, simple in 3-4 lines you can do machine learning prediction. So what it does is it does the feature selection for you. It removes all those columns which are not relevant to predict this level Y trend, and it does the hyperparameter tuning. All these AutoCAD can do. So if we take one further deep example, so this is MNIST database. So they have taken. So here like NumPy, TensorFlow, and from TensorFlow datasets, MNIST database has been taken. MNIST is the handwriting recognition database. So in digits, handwritten digits, it predicts whether it is 0, 1, 2, like that. Here you see like train test. So load data, it MNIST load data, it will this is called a tuple unpacking in Python. So if you have two variables, you are in the left hand side and you are sending, suppose returning two variables, and both are like tuples, so it will get stored here. And further it is again classified, further it is again divided into train. Means these are the extra and right train. Means actually what it does is it splits the data sets into train and test. So if you see the shape means it shows the, the rows and columns. So is my screen visible?
Yes.
Yes,
Okay.
sir.
Okay, thanks. Okay, so yeah, I was here like it provides the shape and the train data type, and here we saw like, so it initializes the image classifier. So we don't need to use which machine learning model or algorithm we need to use. So only we do image classifier and it will initialize that, and it will create a CLF and CLF.fit, and it does the training. And we have given epochs, it's 10 epochs it will do. If in 10 times it will do the end-to-end training. Then we have this predicted y, so it will do the prediction on top of this whatever the training we have done. And further we can do the validation. So validation split also we can do like it is 85-15. So normally we do validation test train means in a single like 70-20-15, 70-15-15, like that. And like, so this is a simple. auto garage example. Similarly, this is auto skleron. So same thing like skleron dataset. It's about breast cancer. So it again it split it into test and train, and you need to auto skleron classifier. So you don't need to specify which algorithm to use. Skleron will find out that, and it's fit will do the training and all hyperparameter tuning. So this AutoML leaderboard, so it will run this training across multiple algorithms, classification algorithm, and it will show like which model has gave the best result. And here you see then show models, it will show the models, and last is the predict one. So similarly, whatever AutoScaling done, we have this same thing in PyTorch also, quite similar. Let's not go here. This is one diagram specific. This is AWS is providing in their SageMaker one product called Autopilot. So you give the raw data. So here this is the X train we have given, and this is the Y train target means the label. And this model creation has been done automatically, and we means that image classifier like we have given, we don't specify whether use logistic regression or any other algorithm. Then it will create a model notebook for you, and like what all AWS SageMaker has tried, and model leaderboard, it will show which all models it has trained with and which are the top four or how many you have identified. And based on that, you can deploy the best one, you can deploy and monitor. So it does all the hyperparameter tuning and all for you. So AutoML has, so this is like you are abstracting this work to the this libraries. So the that feature engineering and ML model selection, these all things it does for you. So here you see it is doing notebook creation. Yeah, here it shows the feature importance, like which column is, if I click like plant type is the more importance to the prediction. If plant type increases or decreases, as per that the label value would changes. So but customer tenure, so this is like a correlation efficiency. So this you can check. And sorry, these are few use cases: price prediction, risk assessment, and all. So this is just an example of AWS. We have same for IBM. IBM has SPSS Auto Modeler. So that also does the all like in a Excel. You can show like which all columns are being used, which are being dropped, and which are has the more correlation with the label. Azure has also the similar things. Basically, all the new cloud providers, they have their own AutoML model pipelines. And yeah, so what means why then we are studying all these things, because these are not tunable. So whatever the this libraries decide, you need to work on, you need to find with that. This is useful for a first solution, but if you want to do further fine tuning, this may not be useful for you. So for the initial POC or a MVP, you can go with this. But you want to go further to increase the F1 score, as was told, then you need to go inside. You need to break down and you need to try it out yourself. um yeah, where was I? And demo. So these are like the overall processes we have told, and what all tools and libraries we can use throughout the machine learning processes. Now we will show one demo and specify like how in that demo it is the tools and libraries are being used. So for that, I'm using this predicting Titanic survivors from the famous Kaggle problem. Like based on these features given, predict that whether that person survived or died in the Titanic accident. Okay. Okay, so first we do import the variables pandas, numpy, and pylab, or you can do matplotlib also. Have used pylab. Then read the CSV. Data collection is done. This is already provided in the Kaggle. So this is a simple CSV file, and df train, and the head we do to it shows the first 5 lines, 5 rows. So we have these columns it shows, and these all things. Then the tail, it shows the last 5 rows. Then the data types of each columns. Like passenger ID is a int 64. Why it is showing int 64? Because it is on behind the pandas. It is based on NumPy. So NumPy is P basis made on top of the C programming language. So C has int 64, 32 like that. So it is showing 64. So object, in the sense, object can be like anything. It's like a generic data type. So for better performance, you can change the data type to here. You can do string, or based on the type, you can do float or integer. So we got a basic idea that what all data types are, the columns are belongs to. Then in info, same. If you see, we are doing this in the same, after loading the data set in df train only, we are doing these operations. Sorry. So info, it is showing like how many entries are there, how many rows are there, and which are like see, all are 891, but age has 714 values. So there are missing values in the age. Cabin has also missing values, only 204 are present. So we have missing values problem are here. And there is another method, describe. So it will show that what is the count. So whatever it shows, the same thing it shows in the first row, count, and all the columns. Then what is the mean value, and standard deviation, and what is the percentile value of this, the max values. Okay. Then this next step which we do is we do exploratory data analysis, which is called EDA in short. So we, to get a better understanding of what kind of data we are dealing with, we generally, before specifying whether we need any data um, pre-processing, or which, whether it is a, what kind of problem is this, classification, regression, or what all columns need to be standardized. And to get all this idea, we do EDA. But the AutoML, that does the EDA for you. So if you see here, we are telling what all survived, and bar chart and date and survival count. So this plot is coming from this line. So survived value counts. So if you see, around 550 people survived, and so this one died, this one is survived. So around, these are the bar charts it is showing. So if we see the uh, survived here, the 0 1, so 0 means died, 1 means survived. So that exact how many are 0, how many are 1, it is showing in this chart. So similarly, this is showing the passenger class. So what is the first class, second class, and third class. So these all things can be found. And gender, how many male, female are there, and how many embarkation count means boats are there. So how many people ride to the boat, that is showing, and the age of all the passengers. So we see many 20 to 30 range of people or more. So these, we get a basic understanding of what kind of data set we are dealing with. So that we do in EDA. Then passenger class. So to then we, what we do is we find the relations between different columns. Like this is the passenger class and survived. So is we try to find out like what is the correlation between the columns. So survive is the actual end. We want to find how many, if the people have survived or not. And this is the passenger class, like whether the class has any correlation with the survived. If it is, if the person is first class, whether he or she has the higher chance of survival. To that, we cross tab, there is a function called cross tab. So 2 columns, and if we do cross tab method and pass the 2 columns to that, so it shows this another data frame it creates, so survived, and this is the value. So this maybe interviewing to understand, we can plot it. So in this plot, you can see like green are the survived, one means survived. So if you see the passenger is of first class, the chances of survival is higher, and third class, the survival rate is lower. Then in this scenario, we understood that there is a high chance of correlation between the cap class and the survival feature, survival level. Then the sex feature. So whether the person is male or female, does it have any correlation? So again, we found out that like um, a gender mapping. First, we have done the gender mapping. I think here it in the data set we have male, female, and this thing. So we and the data type was object. So we want to make it to a boolean value like 0, 1. So it will be int. Uh, So we prepared a mapping wherever the female will be there, it will be considered as 0 and male will be considered as 1. So this dot unique will provide all the unique values of that sex column. And under mapping we have done, then data type we give integer, and these all we do, and we saw that if the if the sex is female, then the chances of survival is higher, and male, the chances of survival is lower. So then the sex has another high level of correlation is there. And this is further like both sex and uh, class we have taken. So if it is first class and uh, female, then there is a high chances of male chances of survival is low, but female chances of survival is very high. These are so this is a good case of how to handle missing data. So if you see here, if we do embarked has around two rows which are not which don't have any value. So how we do is we have done a mapping that nan has give the mapping as 0. So if it is then we have gp it means in the dict we mapped it. So now nan always will show 0, 1 or 0, 1, 2, 3. The impact value will always be 0, 1, 2, 3, and same we mapped here. So these are the number of counts of 0, 1, 2, 3 values of the impact. These are all data pre-processing is going on. Yeah, age. So age we saw initially that around 200 are there, and around 600 rows don't have any age value. So in that case, how we do is we find out the sex. This is like sex, passenger class, and age we have printed out, and we found out like age we have done the median thing. But here we saw if we do the mean thing, mean will come around mostly it will come near 2030. So we have done the median thing. Mean will come here near 2030 because more number of passengers are here. But median we do, it will come whatever the middle value is there. And age is a important factor. So based on the general knowledge, so that's why we need to we can't drop the age column. We have to impute the data of age column. So median value we failed. Um, and family size, not go there. And just a second. Hello, am I audible? Hello?
Yes, sir, you are
Yes.
Yes.
audible.
Yeah. No, no, yeah. Yeah. Um, so this is the whole thing we have written in a function. Because the same thing we need to do, same process we need to follow for the test data also. So this is a clean data. So data pre-processing, entire thing we have written in a function. So the whatever we have discussed, the same thing we have written it here in a single cell. And we have dropped which are non-relevant also. Um, Random forest. Okay, then this is one algorithm, random forest. So random forest have been used. So from sklearn ensemble, we have used random forest. Random forest is like multiple decision trees we ensemble to create the random forest classifier. So we have 100 estimators we have done, and here we have find out the trend features and the trend target. So first one is the survived column. So that we have not included in the trend feature, but we included in the trend target. And see left dot fit is the trending happening. Then the score and the predictions. Okay, here the test predict happened and model accuracy. Um, this one Subhadasi has told, we can find out the accuracy based on Escalon's methods. So metrics methods. What's that? Trend test split is done to split the trend and test dataset. Accuracy score here we have defined, and this is like a more explanation kind of thing. So this is called confusion matrix. So that true, positive, false, negative, true, negative, which Subhadasi has already explained. And this is the formula, precision and recall. And based on all this, so from the classification report, we got how our model is performing. The F score is 0.86. That means it is 86% our model is working correctly. And the precision and recall are there, like how accurate precision, you can say true positives are there. And the recall is how, which are it is missing. So recall is mostly used in spam email detection. Um, yeah. Uh, yeah. Subhadip, you want to take over?
Yeah, I think we have one more demo coming up for a neural network based classifier. So let's jump into it. And after that, we'll have a Q&A session based on how much time we have left. So let's go to the um, demo. Um, Sharing my screen one more time. Okay, so actually I linked the demo here. So it's a collab notebook. So you can, even after this presentation, you can go to this collab notebook and run it. So let's get started. So here, basically, the idea is to, I can make the font size a bit bigger. Okay. Um, so the main idea here is to, before created this demo, there are multiple use cases of neural networks. So the data can be image, the data can be text data, the data can be speech data, and it can also come as just a tabular data, like we just saw the Titanic data set. That was not speech, not text, not image, right? That was just already kind of, we can think of that as a tabular data. So data can come in many forms. So here for the demo, um, the purpose is to show how to handle any kind of data, not just one specific type. So here the data set is created using a by using basically a random function which generates a data on its own. Um, but this demo can generalize to any other kinds of data sets. There needs to be tweaks to handle different kinds of data sets. For example, images and other data sets definitely need a different kind of data loading, but this demo kind of covers a lot of aspects which are general for different kinds of data sets. So let's start with the first step. For any machine learning code, we need to import packages. Here, we this is completely PyTorch based code. We can also write another library code like TensorFlow, but this is only PyTorch here. Um, we also we basically import the NN from Torch. We just import Torch. The data set and data loader, these two are important to be imported because we'll be using them. Um, and we use TQDM for progress bar. We import from TQDM, import TQDM and matplotlib. So since we are already looking at a collab notebook, let me quickly show you how to use a collab notebook. So it's just in Google search, you can type in collab notebook, and it will come up, and you can set which device you want to run the code on by clicking on this and uh, clicking on change runtime type. So right now it is running on GPU. So I don't know if this is visible now. So there are different options here, non-GPU and TPU. So right now I have set it to GPU. So one thing to note is that when we use a neural network, using GPU really improves the training time because GPUs are faster to run neural networks basically. So here, let's look. So this is the only setup that we need to do in Collab Notebook, and then we can start running it. So let me import the packages. Um, Okay, so the packages are imported. This is the dataset class. This is also a bit of PyTorch code, very specific to PyTorch. But the main idea is that we create a or define a class. Here we are calling it my dataset. This is on top of the dataset that we imported from Torch, and here there should be at least three different methods: init, the length method, and the get item method. The idea of the init method is that it should have the X and Y labels. We can be a little bit more flexible on this part as well based on the use case. For example, in some cases, we don't need we don't want to load all the data into memory. Instead, we want to load the data to memory only when we are loading a batch of data. So it depends on the use case. In this case, what we do is we randomly generate um, 10,000 data points. Each has 64 dimensions. So basically, we can think of this as 10K cross 64 matrix, right? And this is generated from a random normal distribution. And this is for a demo purpose. This is not a real data, but we are just randomly generating this data. And we also generate the labels randomly, where we have three different possible classes. Um, and the possible labels are there for 0, 1, and 2. And here we set the size to 10,000 again. So basically, for 10,000 samples, we have 10,000 labels. And each of these labels can be 0, 1, or 2. We define two more functions, the length function and the get item function. The length is basically, we can call this method to find out how many data samples are there in this data set. And the get item function gets the specific X and Y for a given index. And it is basically it gets a data sample from this data set. We can just provide an index and we'll get the features and the label for that index. And
Just
this
just
is
to add here. So here underscore length means that is called dunder length. So this is like we are when we do length of x. So if x is list, so in end it is calling that dunder length method only. So here we are modifying the built-in length with our own specific customized length option. And if somebody will do length of my data set, so it will give them the length of that x self dot x. So it will not give the my data set length. So similarly, the under get item method, so underscore get item underscore. So in that, if we do get my data set something, so it will return the x index and y index. So we are modifying the built-in get item method here. So that's how we are doing here. Yeah.
yeah, so basically these are we are overwriting the already existing methods
Yes.
in this class, the dataset class. Um, but these three methods are important to be there in our dataset class definition. Um, and so there are multiple variations of the same code, but this is a good way to think about the whole dataset code, that in it we define the length function and the get item function. Um, so next, let's go to the model. So in fact, this is the same exact model that we just discussed during the presentation earlier. So this has three different linear layers. Each of them has a ReLU nonlinearity, which follows the linear layer. And the forward function defines the way in which we pass it. The data is passed through the network, through the neural network. So basically, this takes in 64 dimensions. This here is hard coded, as you can see, but this can be generalized by passing arguments as well. Here it is 64. So if we look at the data set that we just defined, it has also 64 features. So this is compatible with this data set. So in a real world scenario, we should look at the data set, identify the number of features, and accordingly set the size of the input layer here. Um, this is the class that we defined. And there is another thing that we can do to basically improve the whole neural network training, is to do a better initialization of the weights of the network rather than just randomly initializing the weights. So this is called Xavier initialization, where instead of randomly initializing the weights and biases of the network, we do a Xavier uniform like initialization, where the weights are much more likely to basically the model is more likely to start learning from a better initialization point than just randomly starting to learn from a very random point in the learning space. Um, so this is an optional step, but it's good to just use Javier initialization in almost all the cases if the model is trained from scratch. Um, we define the model here and an initialization method here. All these are still just class definitions, and these are all class definitions and just function definitions. Finally, we define one other function called the train function, which takes in the model, the data loader, the criterion for computing the loss, the optimizer, the epoch, and the device. We will see exactly when we are calling this function, what arguments we pass. But for now, these are the different arguments this takes in. We first set the model to the training method, which says that all the parameters of the model should have their gradients enabled so that the model can learn with the optimizer in place. And this is important to set while training. And if we are testing the model, we need to use model.eval. We don't show that in this demo because we are just doing training, but the mode in which the model is in is important to make sure that the gradients of the model weights are enabled or not. Then we basically we initialize some variables with some zero scores, because we want to like track them. The epoch loss, num correct, and total all are initialized to 0. We basically create this progress bar here by um, inputting the iterator. Any iterator can go inside TQDM. So data loader is an iterator, and we also specify the description, whether we want to leave the progress bar while training or not, the unit which we see. So this is kind of very much like decorating the code, not super necessary, but we'll see this in action in a bit. This is the for loop which goes through all the batches in a given epoch. So this train function works for one epoch, and if we are training for, let's say, 10 epochs, we should call the train method 10 times. Um, Here we have for the data and label in the data loader, basically, which is wrapped inside the progress bar here. We transfer each and every component in that batch, including the features and the label, to the device. So the device here is basically, it's either the GPU or the CPU. If it is CPU, then the transfer doesn't really happen because the data is already in the CPU to begin with. But if the device is GPU, then the whole batch of data is first transferred to the GPU, where the computations are much faster, and then the computations happen. So the next few steps are probably familiar from what we discussed before. We zero out the optimizer by using optimizer.zeroGrad. Then we do a forward pass, followed by computation of loss, where we pass the output of the model along with the gold labels that we get from the original data. And then we have, once we have the loss, we can compute or we can track the loss for that epoch by just adding it to the previous value. We keep track of this. Then we can compute the prediction from the out. Note that for computing the prediction, we don't really need the loss. So we just need the forward pass output to compute the predictions. Then we can compute the total number of correct in this particular batch by just finding the number of times the prediction and the gold labels are equal. Um, and then we keep track of the number of correct for the overall data set. Finally, we just update the total as well, just to keep track of the denominator if we want to compute the accuracy in the end. Uh, we do the back propagation and compute the gradients by doing loss dot backward. This is one line of code which can be used to basically um, ensure that when the model is learning, the gradients can kind of explode, or they are very very small. So when the gradients explode, for example, one gradient is 10 million times higher than the other gradients, then it kind of nullifies all other gradients. So setting a grad norm ensures that every gradient which is higher than some value is clipped to a certain value. So this makes sure that the learning overall is smooth rather than a very sporadic learning. So it depends on the use case. It doesn't really matter in a lot of cases. So this few lines of code probably won't be really helpful in a lot of cases, but it's a good practice to just keep track of the norm while training. Finally, we do the optimizer step where the weights and biases of the model are changed according to the loss. Finally, we just so there are these are two lines of code which update the progress bar so that we can see. We return the loss and also the accuracy. This is nothing but the accuracy, by the way, the total number of correct divided by the total number of samples. Um, so these are the things which are returned. And then we have, so these are all the functions that we define. Now let's go to really train this model. Basically, we'll go through all the steps uh, from data loading to kind of creating the data loader, followed by model initialization, model training, and finally analyzing how the loss changes during the training and also how the accuracy changes during the training. So what we would expect is that the loss should decrease during the training process, whereas the accuracy should increase. And because this is basically synthetic data or artificially generated data, the model should not find it very, very hard to get to a very high accuracy, like 100%. So let's see if we are getting that in this like run. A few quick notes before we actually run this code is that we can set the random seed by using torch.manual seed and torch.qdam manual seed all. This will ensure that every time we run it, we get the exact same result. Here, we set the device to either CUDA or CPU based on whatever is available in the machine that we are running this code. So if CUDA, which is GPU, is available, so CUDA is not exactly GPU. Uh, it's basically it enables GPU usage. So if CUDA is present, then it will automatically pick CUDA as the device. Otherwise, it will run on CPU. Um, we initialize the data set by just doing data equals my data set. Then we initialize the data loader by doing data loader passing the data set, the batch size in which we want to train the model. Higher batch size is better, but higher batch size also consumes more memory in the GPU. So it's kind of a trade-off between how much GPU memory we have and at the same time how much we can increase the batch size. And here we set shuffle equals true, which means the data samples inside one epoch are all shuffled so that in different epochs the same batch might not have the exact same sample. So this is a good way to like really mix it up, which helps in the training process. We define the model here, model equals my model. Then we transfer the model to device. This is an important step because if we are running the experiment on a GPU, we need to make sure that the model also is on the GPU, which basically means the parameters of the models, the weights and biases are on the GPU. So this step ensures that we do the Javier initialization to initialize weights. It's just one line of code. We just keep track of the model by printing it here. tqdm.write is nothing but print. It's just a fancy way of doing print, which can save to a file at a later stage. But we can actually think of this as just print. Um, we compute the number of parameters in the model. So this kind of indicates how big is the model. And then we define the criterion, the loss function, basically, the optimizer, which is in this case, the torch.optim.adam. All these have different choices. So we can pick from a few choices, but these are good choices to start with. And finally, we go through that for loop, which runs for 10 epochs in this case. So for epoch in range 1 to 11, basically, which is like 10 different iterations, we compute the loss and accuracy, and we save all of this. Finally, we plot the loss and accuracy. So the plot is basically on the x-axis we show the number of epochs, and on the y-axis we show the loss and accuracy. So let's go and do this run from the beginning. I think the runtime disconnected, so let's start it one more time. So I'm basically running each cell that we went through. So it shows that the device that it is running on is CUDA, which means it is running on the it's running on the GPU, which is available in Google Colab. And here we have the model training going on. It trained till 10 epochs, and because we set the leave equals fall, the progress bar does not stay. It like goes away. Let's actually change that quickly. Um, um, so let me do leave equals true here, and so this time the progress bar stays, and we can see that for each epoch, the loss we can see that the loss overall keeps on decreasing right after each epoch. And also we are tracking the grad norm, which is a scalar value. So these are the two things we're tracking. The grad norm is reasonable. It's not like one is 1000 and the other norm is 1 or something like that. So it's reasonably okay. Um, we have, I think these are the only things we're tracking, the loss and the grad norm. So after 10 epochs, it stops. Now it's time to plot the loss and accuracies. So this will take care of this. Okay, so the font size is very weird here, but basically these are two different plots. In each plot, the x-axis shows the epoch, and the y-axis in the first plot shows the loss. In the second plot, it shows the accuracy. And as we expect, the loss is decreasing while the training progresses, and the accuracy is increasing. And note that this behavior is very we see a very solid curve, very straight line kind of curve for both the loss and accuracy. In the real data case, this won't be true. The loss might decrease and increase, but the overall trend would be decreases, and the accuracy would also behave in a similar way, instead of having like a very linear kind of growth or decay. Um, so here we basically trained a model using a neural network we trained a neural network model using a synthetic data set, and we see that the model is working as expected. The loss is decreasing, the accuracy is increasing. And if we have a very huge data set, we can still run the same model and train the model using that data set, which using a scikit-learn based classifier, we would not be able to train uh, on that huge data set. Plus the neural network based classifiers outperform the logistic regression based, or generally speaking, scikit-learn based classifiers in a lot of cases, especially when the data size is big. But having said that, it's important to also run experiments with a wide range of classifiers, including the scikit-learn based classifiers, because sometimes experiments show an opposite trend. It really depends on the use case, the data, and a lot of other factors. So I will stop here. Stop for questions. We can take up questions. I think we are already over time, but we can definitely take questions if you have any.
There is a question in the chat for you. You can answer that.
Okay, I just saw that. So okay, so the question is how we can say that bias and variance is low for data set. Is there any threshold to which we have to compare? Um, Yeah, so basically, there is no particular threshold that I know of, but it's basically a balance. We should try to find a balance between bias and variance. We should aim for a model which doesn't have too much bias or too much variance. We should aim for something which is like a little bias and a little variance. So does that answer your question? Okay, how to identify then? Yeah, I think it depends on different cases, I guess. Um, so the follow-up question from Kusum is that how to identify the bias and variance. Um, so I guess the first thing to do here uh, is to change or basically do experiments with different hyperparameters, I guess. And this is not specific to deep learning models. I think this can happen to any machine learning model. So it's I recall this a lot in regression experiments where the fit line kind of we clearly see that there is more variance or more bias. So I would say how to identify them. The answer to that would be to try with different hyperparameters and based on the development set scores, pick the best model. So hopefully that answers the question. But yeah, thanks for the question.
Actually, my question is that uh, I read actually the many blogs also that we have to find the balance between bias and variance. So my question is how to identify that there is a balance between bias and other variable, that variance.
Yeah, so if your question is about how to quantify the bias and the variance,
Yes,
then
yes. Yeah, I
then
know how to calculate the, I mean, variance and bias, but my question is that how to find the balance between these two? Matlab, how can I identify that there is a balance? I mean, so that I can find that this model is good enough now. Like
uh,
value, is there any value? Like for example, variance is 20 and bias is 30. So I have to identify na ki there is a balance between these two or not.
yeah, so I think there are different ways in which you can like think about this finding the best model. What I would do is instead of like I would definitely try to balance bias and variance, but what I would really try to do is look at the development metric. Like if the development set accuracy says
Okay.
that pick the model which has a very high variance and very low bias, I'll pick that in any way. Like I will rely more on the development set metric rather than actually, for example, making sure that the average of the bias and variance scores is the minimum. So
Like
that's
for
more reliable.
example, the my matrix is precision, recall, f1 score, and accuracy also. Like, because when we are developing a model, then they also tell us na accuracy according to that in the during the train time. So we have to consider accuracy or precision, recall, or f1. I mean, the value of these we have to consider, or we have to consider only one metric.
I think it depends. Usually, it's okay to just use one. For example, F1 score,
Okay.
um, because F1 score kind of takes into account the precision and recall, right?
Mm-hmm.
So it usually is not necessary to combine all this. Just looking at the F1 score is enough, but just for a sanity check, it makes sense to also just tally the accuracy and make sure that it's not too off.
Okay.
But having said that, like there are many methods you want to fine tune. Suppose your F1 score is low, so you want to check whether precision is low or recall is low. Suppose you are detecting spam in email, so in that case your recall should be very high. So precision may not matters that much. So in that case, you can a specific stats means precision or recall. Recall will be more valuable there rather than F1 score. So based on the scenarios, it varies. Okay, there is one question for Javier initialization. You can answer that.
Yeah, so thanks for this question. So the main idea behind, there's a paper about Xavier initialization which talks in, like, which really deep dives into the idea of Xavier initialization. But on a high level, basically the idea is that um, instead of starting from a very random initialization of weights, we start from an initialization which is more suitable for the neural network to learn. Let's consider like an initialization where all the weights and biases are set to 0, right? In that case, the model, whenever it's trying to learn, it's computing the gradient from 0. So the delta is computed basically, when computing the delta in the gradient, it's 0 minus 0. So it basically becomes 0, and the model never like kicks off training basically. So Zapier initialization on the other hand makes sure that this never happens. This initializes the weights and biases. I'm not 100% sure, but I think it's based on a normal distribution, so that all the values of the weights and biases are not concentrated on like a 0 score or some other score. So that's how Xavier initialization is useful, and that's the general idea behind that. There are definitely other techniques to initialize. I'm not super familiar with them because I always just, it's standard practice to go with just Zapier initialization, but it makes sense to look for other initialization techniques and find out how it's different. Yeah, I'm not familiar with all the other techniques, but you can definitely check it out.
So any other questions from the participants? I think we don't have any further queries.
Okay.
So I guess we'll be sharing the slides with the links. So if you have any questions even after this, feel free to reach out. And yeah, I think we have linked all the resources that we showed to the presentation. So it should be a one-stop resource.
So thank you, Suven.
Thank you, sir.
And maybe now we can end this session. So that we can start the next session. And at the end, I'll ask Kusumlata madam, I was listening to the question. First thing is that if you have small data set, you should not apply deep learning methods, because many times even I told that deep learning methods are not for less data set, because in the traditional method will be very, you can you can get good results. So deep learning methods, only you have millions of data, then only it can able to perform, and otherwise it will be, you'll never get a satisfied results, and many times also you feel the difference. Yeah, so and another thing that if your data set is low, maybe you can try to use some data augmentation approach, where you can try to add the data, so like some synthetic data, or you can generate some data, and so that if you really want to go for deep learning methods, then you can increase your data set using this kind of data augmentation, and then you can evaluate a performance that okay, up to how much data your accuracy is increasing or you are really degrading. That's why nowadays people do a lot of this data augmentation. So maybe that will be different things to discuss. So I don't want to involve much, but yeah. So thank you, Somendra and Subhadarshi. So now I'd like to request the session chair to declare the end of this session and announce the next session. Thank you.
Thank you, Somendra sir and Subhadarshi sir, for delivering your valuable talk on machine learning and tools. Thanks a lot for being there with us.